Okay, this is Introduction to Trigonometry and revolves around angles and degrees. And so you can divide degrees into tenths of degrees. And if you know on the Earth, though, we've got degrees of longitude and degrees of latitude. So longitude goes this way, latitude goes this way, and it's a long distance for each degree. So they've subdivided it into something that's more degrees like. Instead of tenths, which are nice for math, they're way nicer. But we have this thing called degrees, minutes, seconds. So a 60th of a degree is a minute. A 60th of a minute of a degree is a second. And so we abbreviate this DMS with all capitals. So you can see DMS in your book. You'll see it probably on tests. And we're going to do some conversions. So example one we're going to convert from degrees, minutes, seconds or from degrees with a decimal, 37.425 degrees. That's part A. 2 degrees, minutes, seconds. Well, it's 37 degrees. Maybe I can write 37, not 30. 37 degrees. To do the minutes part, I'm going to do 0.425 times 60, which equals 25.5 minutes. Okay, 37 degrees, 25 minutes. Minutes we're going to use this line for. It's kind of like feet. And then we'll use, again, what's after the decimal times 60 again, 30 seconds. So 37.425 degrees is 37 degrees, 25 minutes, and 30 seconds. And that's what my answer looks like. We're going to go the other way in part B. 42 degrees, 24 minutes, and 36 seconds. So I know it's going to be 42 point something. So I'm going to take those minutes, 24, and I'm going to divide by 60, which gives me, they didn't. "24 over 60 is 0.4. "36, it's over 60 seconds. That would put me in minutes, but over 60 again. So I'm going to go over 60 squared, which is 3,600. Is 0.01. So here I'm adding those up. 42 plus 0.4 plus 0.01 equals 42.41 degrees. There, I've converted back and forth. Okay, that's degrees, minutes, seconds. Pretty simple conversion, pretty straightforward. Not too tough of a concept. We are going to talk about direction and heading in this chapter as we introduce trigonometry. And we'll get into more advanced trigonometry as we go. But we're also going to apply it. Trigonometry is all theoretical math, but it can be applied to real world. And you've probably heard of something called bearing. And bearing is a measure of direction as you travel. Bearing is measured from due north. So this is due north. If I am going this way, and this measure here, I always go clockwise for bearing, is 155 degrees. That's a bearing of 155. If it's over here, it's measured clockwise from due north. That might be 285 for a bearing because it's 285 degrees. Okay. Again, the second arrow is the direction I am traveling. Now, you are used to measuring angles in terms of degrees. You've been doing it since you started measuring angles. I don't know when you started measuring angles. I don't teach elementary school. I don't really teach middle school. So I don't remember where you learned to measure angles. But you've been using degrees. And degrees are nice. There's 360 degrees in a circle. We all know that. Okay? Um, didn't mean to go back that far. Just meant to clean my screen. So there's another way to measure angles, and it's what's called a radian. And a radian is equal to the arc length across my arc divided by the radius. So let's say I've got this. I got a radius of 3, and this length is pi. Now I'm intentionally doing pi because the circumference of a circle is equal to 2 times pi times the radius. My arc length is pi, this length. So the angle is pi divided by 3. We have this thing that we'll be introducing later, but it's called the unit circle. We'll go into more depth on this. It's a circle of area of radius 1. Okay, the unit circle. Radius equals 1. Radian measure is the length of the arc of an arc of the unit circle. Okay? And it scales out because the angle doesn't change if I make this longer and put my circle out here. Let's do that in a different color. If I put my circle out there, or my section of circle out here, it doesn't change the angle. That's why we divide by radius. Radians work better in higher level math. I still think in degrees. I've been doing this for years. I can convert. And the mathematical formulas work better with radians, which is why we like radians. It's why we have another measure. Okay? Especially the calculus. Once you get to calculus, the calculus formulas, I've never known how to make them work with degrees. I think there's a way, but it's more complicated. It's often easier to just convert to radians, do everything in radians, convert back to degrees at the end, if you want it in degrees. So if I've got this circle of radius 1, the circumference of this unit circle, 2 pi times 1, is 2 pi. Oops, times 1. So that's just equal to 2 pi. So once around the circle is 2 pi radians. That means 2 pi, 360 degrees is equal to 2 pi, or 180 degrees is equal to pi. So if I want to convert from degrees to radians, we're going to do example 2 here. I multiply by pi over 180. My conversion factors are pi over 180. Radians should always be less than degrees, or 180 over pi. Usually radian measures have a pi in the number, so the one that keeps the pi instead of cancels it out, that would be pi over 180 is how I remember to convert. Example 2a, we're going to do 90 degrees to radians. All I do is multiply by pi over 180. That's 90 pi over 180, and I reduce that to 1/2 pi, or pi over 2. I just don't write the 1. Part B of this, we're going to convert the other way. Pi over 3 radians, we're going to convert to degrees. My pi's cancel here, leaving me with 180 over 3, which equals 60 degrees. Okay. Find the length of an arc intercepted by a second central angle of 1/2 radian in a circle of radius 5. So, well, I know radian is equal to arc length, which is, well, I asked for the length of the arc, that's arc length, divided by radius. So, line here. Let's do it that way. 1/2 equals, S is what we're going to use for arc length. Radius is 5. That's too close. So 2.5, multiply both sides by 5. 2.5 is my length. We end up with, I'm not going to do D. We end up with this formula, theta r. So I've multiplied both sides. For radian measure, we use the Greek letter theta. That's this right here. I think that's how you spell it. Theta in it, represents angles. You probably used it to represent an angle at some point. But it's angles, and for this purpose, it has to be in radians. I think in integrated 2, I define it as 2 pi r theta over 360, which I can reduce to, actually, I know how I define it. X would be my angle in degrees over 360 times 2 pi r. So 2 and 360 cancel. X over 180 pi r, which pi over 180 is my conversion factor, radians to degrees. If X is my angle in degrees, I can just replace that with an angle in radians r. And so that's another way of thinking about it. So we're going to look at example 3, perimeter of a slice of pizza. Find the perimeter of a 60-degree slice of pizza. It has 7-inch radius. So a slice of pizza looks like this. 7-inch radius, those are both 7. And I need this arc length. This is 60 degrees. So let's convert our degrees to radians. 60 degrees times pi over 180. 60 over 180 is 3 on the bottom, or 1/3. So pi over 3. S equals theta. There's my pi over 3 times my radius 7, which is 7 pi over 3. So that's my outside length here. That's this. My perimeter is the total distance around. 7 plus 7 is 14. Plus 7 pi over 3. You probably don't want it as that. You probably want to use a calculator. It's going to be close to 21. So I just did times on accident, but I got 102 and I knew that couldn't be legitimate. I know pi divided by 3, pi is 3.14 approximately, so this is close. Pi over 3 is close to. This comes up to 21.33 inches. And that's my total perimeter. Okay, designing a running track. I'm a track coach. I like this. So we've got the running lanes at Emory Sears Track at Bluffton College are 1 meter wide. The inside lane is radius 33 meters, and the second lane is inside radius 34. So I've got, like, say the corners on a track. They look kind of like this. This one's 33 meters. And the outside of the first lane is the inside of the second lane. That one's radius 34 meters. And we do have an outside to lane 2, but when you're running, you're allowed to use the inside. So we measure our distances based on the inside of each lane. Lane 1, lane 2. So how much longer is lane 2 than lane 1 around one turn? So, well, we know we're half of a circle, right? So that half of a circle, 180 degrees, let's convert to radians, times pi over 180. Oh, that's pi. That's really a nice, easy number. Easy-ish. My arc length is 33 pi for length 1. So arc length 1, arc length 2 is 34 pi. How much longer is the difference? 34 pi minus 33 pi is, the difference is pi, or approximately 3.14 meters. Okay. Pretty straightforward. Now's when it's going to get a little less straightforward, and we're going to do some physics applications. We're going to talk about angular speed. If I use the word angular, angular means rotational. So we're talking rotational speed. How fast does it rotate? Now, the common thing you've probably heard is RPMs, which stands for revolutions per minute. Those of you that have a car that maybe has a tachometer, tells you how many RPMs, how many times is your engine spinning the shaft that's coming out of it. Revolutions per minute. Per could also be divided by or over. So here's our example. And we're going to use some conversion factors, and then we're going to use that S equals theta R idea still in this problem. So Albert Juarez has a truck that has wheels of 36 inches in diameter. I'm just going to use radius of 18. If the wheels are rotating 630 RPMs, oops. Find the truck's speed in miles per hour. So I'm trying to get to miles per hour. Essential, let's write it. Spot. Miles per hour. Okay. So I know that well, we'll get to this. So we're going to start with 630 revolutions. And radians are essentially unitless, but I know each revolution that's a full circle is 2 pi. Again, it's the angle measure of radians is based on a circle of radius 1, and all those angles are the same. So 2 pi is the circumference of, so it's 2 pi per 1 revolution. So now I've converted to radians. I want to multiply that by the radius. I have 18 inches here for 1 radian. That's a little bit of a strange conversion factor there. So revolutions is canceled out. Inches, I need to go inches to feet and then to miles because I don't know the inches to miles conversion factor. But I know there's 12 inches in 1 foot. And I know there are 5,280 feet in 1 mile. So now I'm in miles. I'm doing these. Notice that inches is canceling. One's on top, one's on bottom. And now, finally, I need to go to hours from minutes. Nope, backwards. Hours needs to go on the bottom. Minutes needs to go on top, so it'll cancel with the minutes at the beginning. That cancels here. 60 minutes and 1 hour. So when I do this, I get 630 times 2 pi times 18 times 60 over 12 times 5,280. I do that on a calculator. I get 67.47. Oops, 67.47 miles per hour. Or I can write that as 67.47 mph for miles per hour. So that's angular speed. We're just using conversion factors. Let's go back for a second. Conversion factors like I've used in the past, I've taught you before. Everything must cancel. And then functionally I'm using this is theta here. This is r. So I'm using s equals theta r, but then I'm having to do the rest of it in conversions to get it into a unit I want. Finally, we're going to talk about nautical miles. You've probably heard this term speed measured in knots. Knots are a nautical mile per hour. And a nautical mile is similar to a regular mile, a statute mile. Statute mile is considered a regular mile or a land mile. A nautical mile is measures 1/60th of a degree of a line of longitude at the equator. Its intercepted arc is 1 nautical mile. So yes, it is an arc. It's an arc length because the Earth is a sphere. So a statute mile, 5,280. And that's how they're going to refer to it. It's approximately 1.15 regular miles or statute miles. So we're going to do a problem with some conversion with this. Megan McCarty, a pilot for Western Airlines, frequently pilots flights from Boston to San Francisco, a distance of 2,698 statute miles. Captain McCarty's calculations of flight time are based on nautical miles. How many nautical miles is it from Boston to San Francisco? So we know the radius of the Earth is approximately 3,956 miles. I'll use N miles to abbreviate nautical miles. And I know 1 minute. So I'm going to convert 1 minute. That's what a nautical mile is, a minute or a 60th of a degree. So that's the same as a minute. And I'll convert that to radians to get my arc length. And this is pi over 1,000 or 10,800. So that's my radian measure for 1 nautical mile. Okay. Now I can just use S equals theta R. 3,956 times pi over 1,800, which gives me this conversion of approximately 1.15. And that's how you develop that per nautical mile. So we know she is going 2,698 miles. So my conversion factor, I got to flip this. 1 nautical mile per 1.15 miles. Or I can literally take this and use my conversion. If I want to be really accurate, I'm going to do 10,800 over 3956 pi miles per nautical mile. And that's going to equal 2,345 nautical miles. I'm just using N miles to abbreviate that. And that is section 4.1.